Okay, welcome back, guys. We are continuing with our material. Now we're going to transition into a bit of a shorter unit, all about the immune system. Um, Again, it's kind of like an overview. We did some stuff regarding immune system in circulatory system, but now we actually get into it a little bit more in depth. So that's kind of exciting. So what are the goals for this unit? Understand the differences between viruses and bacteria. I cannot tell you how many people, unfortunately, don't know that there are key differences between the two. Comprehend the defense of the body or the defenses of the body. So there are a number of different defenses that your body can do to protect itself. And finally, analyze how vaccination works. Better understand why vaccines are as pivotal and important as they are. They've allowed for modern medicine to be as successful as it is, and really to allow us to live to the ages that we can. So very, very important stuff that we're going to get to in the end of this particular unit. Okay, so off the bat, what is a cold? What is a common cold? What is this stuff? A cold is an infection of the mucous membrane, so typically going to be your nose. Um, as regards to that, it's going to be associated to a rhinovirus. So rhinovirus is a family of viruses that exist. I'm not expecting us to know all types of rhinoviruses. That's just not realistic. But you should know that there are a number of these guys. Over 100 rhinoviruses have been identified, one which honestly is one of the big reasons why it's so difficult to build up an immunity. When you get a common cold, right, you expect afterwards, like, oh man, that sucked, but now I feel better. I hope I have some immunity built up. I should be okay. The concern is, since there are so many types of rhinoviruses that exist, and the symptoms for all of them are very similar, then you're going to get sick and get sick again. You get a different strand of a rhinovirus. So that's what makes it so challenging as far as how difficult it can be to work with it. Next, viruses versus bacteria. Let's understand a little bit more about that. So, in regards to viruses and bacteria, viruses are going to be these non living structures. So, first of all, colds are going to be viruses, of course. They're going to be rhinoviruses, as we just mentioned. Influenza is another type of virus. We commonly refer to that as just flu. Um, these are going to be caused by viruses. Here you can see what a rhinovirus looks like. Here you can see what an influenza virus looks like as far as a computer rendering. So viruses are non-living. That's what we observe. I'm actually going to type this. There you go. They're non-living particles that contain genetic material, hijack your cells in order to reproduce. So why do we call it non-living? It doesn't fall under the rules of a living organism. It doesn't have a nucleus. It doesn't metabolize effectively. It doesn't reproduce on its own. It needs a host to take over, and then it can reproduce. So that's one of the unique traits about a virus. They're very, very ancient, super old, just like bacteria, very, very old as well. Let me actually delete this too. I didn't realize extra period unnecessary. Okay. Another important thing to comprehend. So this is big stuff here. This one right here. Viruses cannot be killed with antibiotics. Very important. I cannot tell you how many people believe that a viral infection, like a common cold or a flu, you just take some antibiotics and you're perfectly fine. Antibiotics are just for bacteria, for bacterial infections. Viruses can be treated with antivirals. However, antivirals are not as common as an antibiotic. You don't have as many antivirals that exist. So, more than anything, what can be useful for treating a viral infection is rest. Let your body recuperate, let your body fight. You can take medication to help deal with the symptoms and to help deal with the things that you're experiencing, like the negative side effects. But at the end of the day, if you give your body time, it should be able to fight it off on its own. What about bacteria? So, as far as bacteria are concerned, bacteria are living organisms. So, unlike viruses, they're considered living. They have a metabolism, they have their own DNA, they can reproduce on their own, just like our cells, right? Our cells can do all that stuff through mitosis. Ancient cells, like I said, the earliest species or the earliest creatures that ever lived on this earth were bacteria, single celled organisms, prokaryotic bacteria to be more precise. Um, Bacteria can be killed with antibiotics, like we mentioned in the last slide, because these substances target key processes in bacteria, such as production of bacterial cell wall. So, a antibiotic, it doesn't always attack the cell wall, but an antibiotic enters your body, you consume it, you absorb it into your bloodstream, and when it finds the bacteria that it's targeted for, it's going to attach itself to the bacteria and then destroy a key component of the bacteria. So for instance, if it destroys the cell wall literally holds together all the organelles. So now all the organelles are just going to exit out of the system or of the bacteria, and that could kill the bacteria. So that's why antibiotics are so effective. You do want to make sure though that you consume, like if you're given a prescription, for instance, for strep, which is this bacteria down here, causes streptococcus. If you're given a prescription for strep, you want to make sure you take the antibiotic for the entire regimen, because even if you're feeling better, let's say it's a 7-day prescription, and on day 5 you're feeling better, the concern is your body may not have won the war yet. You're still fighting, and it's on the end of it, but you want to keep taking this for as long as you need to. You don't want overconsumption, of course, but for as long as you need to. E. coli is another very common bacteria. You may have heard of E. coli, especially from outbreaks at different restaurants that occur. Um, we actually have E. coli in our system naturally. So E. coli is pretty normal. It's just normally we have it in your large intestine. It helps with the fecal matter process. Okay, what about the body defenses? So how does our body defend itself? There's different types of defenses that we expect. So there are actually 3 defenses here. We have the non-specific external barriers, which is the first line of defense. We have the innate immune response, which is the second line of defense. And then we have the third line of defense down here called the adaptive immune response. The non-specific barrier, I try to think of it in like very medieval terms because it just makes most sense to me. So the non-specific barrier, I think of it like a castle wall. You build up these walls to protect it against invaders that are trying to attack. What is that wall for our body? Your skin. Your skin, your mucus as well does a pretty good job of preventing any further access, right? But the thing is, those barriers can be penetrated. They're not perfect. So if those barriers are penetrated, the body will then resort to this innate immune response, which is the second line of defense. That's going to be phagocytic cells, natural killer cells, inflammation, fever. This is still considered non-specific. Your body's just doing whatever it can to fight whatever's infecting you. In that circumstance, in relationship to the medieval era analogy I was giving you, if the walls are the first line of defense, the second line of defense are the archers on the very top of the walls and the guys pouring the oil over. They're doing their job to fight the people who are actively invading you. Finally, if the innate immune response is insufficient, the body responds with the adaptive immune response. So in the case of an invading force, like in the medieval circumstances, so this is your cell-mediated immunity and humoral immunity. So in the case of like an invading force, they've surpassed the archers. You know, they've gotten into the walls, they've breaking the gates down with battering rams. All you got left are the soldiers inside. The soldiers inside are the ones trained, you know, in using swords and spears and all these weapons, and they're the ones that are going to fight to defend the people. Which that's kind of how the immune system works. A very similar concept. All 3 of these stages we're going to talk more about in the coming days and the coming videos that we're going to go over. But for now, let's start with that first one. First line of defense. As far as the first line of defense is concerned, it is the non-specific defense, like we mentioned earlier. It is designed to prevent infection by viruses and bacteria. That includes intact skin. So again, intact is the key word there. If your skin is damaged, that is literally now a shortcut for bacteria and viruses to infect you. Mucus and cilia. As far as the mucus and cilia are concerned, we learned about that in respiratory system. That does a decent job of protecting your body. And then finally, phagocytes. You may remember that prefix phago. We talked about that in circulatory system. Phago refers to phagocytosis, which is basically this whole eating process. So this whole eating process is the method in which your body is consuming foreign bacteria. Literally, phagocytes just eat up any foreign bacteria like Pac-Man. That's their whole job. Now, this is all review from integumentary system. You should remember this from our quarter 1 integumentary content. That's the hope, at least. Dead skin cells. So how does this work? How does the skin help your immune system? Dead skin cells are constantly sloughed off, so they shed off, right? Making it hard for invading bacteria to colonize. So that epidermal layer, the very top layer of skin, is constantly shedding. Because it's constantly shedding, the bacteria that you find on your skin falls off very rapidly. It's hard for the bacteria to actually stay there and find like a home or colonize, as we call it. What about the stuff inside your skin? So in your dermis, you have the sweat glands and the oil glands, like the sebaceous gland. The oil glands are a little bit more important here. The sebum, which is the oil that is secreted, acts like an antimicrobial. It is a natural antibiotic. It's a natural antibiotic. I know we have a love-hate relationship with the oil glands because too much oil and specifically an infection of the oil glands can cause acne. That's something we don't like, but the oils are good for your body overall. That's kind of the idea, right? Sweat glands are not necessarily as big for the immune system, but when we sweat because we're hot, you're going to secrete sweat and it's going to drip down your skin. As it drips down your skin, that is going to catch any sort of bacteria or viruses that are in the way. So it kind of acts like a natural response for the immune system. Role of mucus and cilia, this is all stuff from respiratory system. The mucus is going to contain, and we have most of our mucus in the nasal cavity. You do have some mucus in the pharynx and then also in the trachea, but most of it in the nasal cavity. Mucus is going to contain lysozymes, which these are special enzymes. You may have learned that in other classes like AP Bio if you've taken that, which are going to destroy bacterial cell walls. I like to think of lysozymes like baby versions of immune cells. They're not cells, but they're like little enzymes that help to destroy and chunk away at bacteria. The normal flow of mucus washes bacteria and viruses off of mucous membranes. And what helps with that are these cilia. Remember, we talked about cilia. You find them inside the trachea. They're microscopic hairs. The cilia in the respiratory tract move mucus out of the lungs to keep bacteria and viruses out. So they actually grab onto mucus, and guess what's on the mucus? Because it's like a glue. It's going to grab onto bacteria and viruses, and then you're going to expulse it out of your system in hopes that it never infects your lungs. Is it perfect? Far from it. This filtration system is not ideal, but it's better than nothing, right? Role of phagocytes. So, as regards to the phagocytes and what they do, remember phagocytes are going through phagocytosis. They eat other cells. So, many white blood cells or leukocytes are going to be considered phagocytic. So, that includes like your macrophages, that includes your neutrophils. We talked about those before. They seek and destroy invaders. They're trying to hunt down anything that is not supposed to be in your body, a pathogen, as we call it. Some also destroy damaged body cells. So if you have a cell that has been damaged, it's also going to try to go out of its way to take care of it. I know that sounds a little cutthroat, but that's kind of what has to happen for your body to function. Phagocytes are attracted by an inflammatory response of damaged cells. So that inflammation is what we see here. When you have inflammation, it's typically signaled by histamine. You have these mast cells found in the skin in many different parts of the body, but they're usually found in layers of skin, and they secrete histamine. You have other cells that secrete histamine too, which we've talked about in the past. Histamine causes fluids to collect around an injury, and it's going to dilute the toxin, so it's going to make the toxin less potent, but it also causes swelling. Swelling is not necessarily a bad thing. Swelling can cause the temperature of the tissue around it to rise, which kind of creates like an oven scenario, and that can kill off bacteria and germs and viruses. But swelling can also be a bad thing if it's too much swelling. Take, for instance, the allergic response. If you have a lot of swelling in the neck, for instance, that can make it very difficult to breathe, and thus it can make it fatal. So you want to be careful with how much swelling your body has. A decent amount of it, not a concern. Too much of it, especially due to an allergic response, can be problematic. Finally, fever. We were talking about that whole oven situation. You're increasing the temperature. Fever is a defense mechanism that can destroy many types of microbes. Fever also helps fight viral infections by increasing interferon production. We don't talk too much about interferons, but they're helpful for the immune system. While high fevers can be dangerous, some doctors recommend letting low fevers run their course without taking aspirin or ibuprofen. So, what do we mean by that? First of all, just remember that your normal body temperature that we like to be at is 98.6 plus or minus 1. That's your happy range. That's where things work ideally. Now, let's say you have a fever of like 100. Anywhere from 100 to 101 is a little hot for your body, but that could be that your body is fighting something right now and it's trying to literally sweat it out. So that could be one of the reasons. At that point, you don't necessarily need to take an ibuprofen or an aspirin or something to help lower a fever. As it starts to climb, though, that's when you want to be careful. Because unfortunately, yes, the body will kick off a fever, but some viruses and bacteria are very efficient and they will adapt to that higher heat. So then your body's like, okay, it's at 101 and the virus is still existing or the bacteria is still living. Let's turn up the heat more and see how you like it. And sometimes those bacteria and viruses can still survive. So now you're looking at 102, 103, 104, 105. And once those temperatures spike, the problem is your internal organs are now not functioning that well. You're boiling everything up. the brain, if you were to die from a fever, it's not because you melt inside or anything like that. It's just the brain cannot work at that hot of a temperature. If you ever get hospitalized, or you're in an ER or an ICU or whatever place, they're going to literally throw bags of ice around you and on you to try to cool your body off as much as possible. Finally, this is a great picture just showcasing the procedure of this whole first line of defense that we were talking about. So let's say you get a splinter. They're unfortunate, painful as well. A splinter is not only going to be covered in bacteria, but the skin itself had a ton of bacteria on it. So now that bacteria is going to enter through the wound, right? The wounded cells of the skin are going to release chemicals to activate the mast cells. The mast cells are then going to secrete histamine. Histamine is then going to enter the capillaries, which, remember, we learned that in cardiovascular system. Capillaries are going to increase blood flow, which is going to also make the heart beat faster. And it's going to increase permeability. Permeability has to do with how well things move in and out. Because of that increased permeability, the phagocytes found in the blood cells are going to secrete outward and start attacking the bacteria. They're going to attack the foreign pathogen. So they do a good job of trying to limit the spread of infection, but they're not perfect. Many times this site of infection is going to allow for things to sneak past and try to create an infection later in the body. But the good news is you have a second line of defense and even a third line of defense that we will talk more about in future videos. Okay, so that was a great one. Overall, just kind of getting us started with this material. Well, pretty short, generally speaking. It shouldn't be too long as far as overall how long it's going to take us. Okay, so thanks for tuning in, guys. I'll see you guys on the next one. Have a great day.